Today I want to tackle this more challenging integral. So it's actually beyond the IB curriculum, but it combines a lot of the skills we already learned, such as integration by parts, completing the squares, and knowing how to apply some standard integral formulas in the data booklet. This question is also very good because it will teach you a new skill called partial fraction decomposition that I think you will learn later than IB. So although it's harder than any test questions you'll encounter, it's really good to learn how to integrate all of the skills together to solve a more complicated problem. So why is this problem complicated? It's because this thing is a complex rational expression. You cannot directly integrate it using like a formula for the formula booklet because, well, you don't have something like 1 over x to the power of 3, right? That's really easy, right? So like here, the denominator is a complex polynomial. It's a sum, right? So you cannot directly integrate it. You have to make it simpler. You have to break this fraction into a bunch of simpler fractions with lower degrees. Then you try to integrate it, like using natural log or using U substitution and using some formulas in the formula booklet. You need to first simplify this. And so the first skill we will learn is how to apply the partial fraction decomposition. Before jumping right into the question, I want to quickly show you what partial fraction decomposition should look like. So let's say we have another complex rational expression that looks like this, with a polynomial in the denominator. Well, we can rewrite the denominator into the product of x minus 3 times x plus 2, right? So that actually equals to, well, let's say a over x minus 3 plus b over x plus 2, right? Yeah, so like we can look at it in another way, like if we multiply a by x plus 2 and also the denominator by x plus 2, then for b we multiply the top and bottom by x minus 3. Hopefully that makes it easier to see why we can break this apart into two sums. So actually, we have the same thing here on the left side, right? And here, since they have the same denominator, we can just write a times x plus 2 plus b times x minus 3, and that entire thing over x minus 3 times x plus 2, right? So like the logic is consistent here, and now we're just writing it in another way. We can get rid of the denominator here, so that means 4 equals to a times x plus 2 plus b times x minus 3, right? So what's the goal? Our goal is that we want to find out what's a and what's b numerically to satisfy this relationship and to ensure that this complex rational expression can be broken down into this perfectly. So after you just try to substitute some numbers and manipulate the results a little bit, and keeping the equal signs equal, you end up a with 4 over 5 and b equals to negative 4 over 5, right? So like you find the a and the b that satisfy this relationship. So that will make this polynomial simpler into this like x plus or minus something. So that's how the basic partial fraction decomposition should look like. Let's apply partial fraction decomposition to this. So in the denominator we have x cubed plus 1, which equals to x cubed plus 1 cubed. We write it like this because we want to factor it, right? So for anything like a cubed plus b cubed, we have a formula like a plus b times a squared minus ab plus b squared. So for this one, we have x plus 1 times x squared minus x plus 1. So we can rewrite this complex rational expression into this new factored form. And since we are applying partial fraction decomposition, we need to solve for, remember, like a and b and stuff like that, to be able to break it into simpler fractions. So we have a over x plus 1, then plus, actually for this one it should be bx plus c. I will explain why. In the denominator we have x squared minus x plus 1. So each one inside this product will be located to one of the smaller fractions. So notice that for this one we have a linear expression. So we have a constant a right here. It's just a number. A is just some number. And for here we have a quadratic expression. So on top of this quadratic, we have a linear expression here, where where b and c are also constants. That's because, like, if we say we multiply the denominator and numerator, multiply them both by this quadratic expression, then the top will have the highest power of 2, right? And if we multiply this fraction's numerator and denominator by x plus 1, like this, by x plus 1, then we want to also end up with the highest power of 2 in the numerator, right? So we have to have a linear expression here. This is linear, this is linear. Together, they will make a quadratic one. This is constant, this is quadratic. Together, they will make a quadratic one. So, like, we need to keep that consistent. So here, it becomes bx plus c. So the denominator, you can see, always has a higher power than what's in the numerator when we're doing this partial fraction decomposition thing. So if we, according to what I just said, multiply the numerator and denominator by this, and for the second fraction, multiply the numerator and denominator by this, we can have something that will help us solve for a, b, and c. So now we just have 1 right here alone, and then for here we have a times x squared minus x plus 1, and plus bx plus c times x plus 1. That's because I got rid of the bottom, and the bottom for each of these fractions, because they are all just equal to this product, right? So I just got rid of the denominators. So now we can start solving for a, b, and c. And I solved a first, then b, then c. And let's see how to do that. So there are actually many ways to solve for a, b, c. But if you just try to set up some values for them, and then, and then try to change them around until somehow they just equal to 1 together, that will be really time consuming. So for this occasion, we can start solving from the highest powers, like for a, by, let's say we can set x equals to -1. Let's see what will happen. So we will have 1 equals to a times, we have 1, plus 1 plus 1 plus I have negative b plus c, then negative 1 plus 1. Well, setting x equals to negative 1, get rid of b and c, because now this equals to 0, right? So we only have this part that matters. So we have 1 equals to 3a, a equals to 1 over 3. So we can use 1 to solve for b and c. Sorry, we can use a to solve for b and c right now. So we're doing this to get rid of the other unknown variables and focus on solving one variable so we can solve it very efficiently. We can do so by just setting x to a certain value so that we can make the terms related to the other variables equal to 0. So we only have 1 and a something something, so we can solve for a. That's a trick to know. So notice that b is also involved in the highest powers here. So what we can do is that we can combine the terms of x squared, because x squared is the highest power. We can combine the terms with the highest powers and use a to solve for b. So what I mean is that, so solve b. The highest powers is just ax squared, right? And now we have bx times x, so that's plus bx squared. Notice that finally, like here, this is like the final answer. We don't have anything related to x squared, right? So that thing equals to 1. So this equals to 1. And we already know that x squared over 3, well, we just substituted a here, plus bx squared equals 0, right? So that means b must equal to negative 1 over 3. Now we know a and b, c will be solved really easily. However, like another really simple way to solve it is that since c only cares for the constant terms, well, not only, but like it usually cares about like the lower degree terms, so we can try to use that to solve for c. So notice that a times 1 is just a, right? And then c times 1 is c. And these are the only two constant terms on the right side. So here and here. And all the other terms have something related to x, right? So this means if we want to solve for c, we can set 1 equals to a times 1 plus c times 1, which is a plus c. That's because the final answer is only a constant term, and it must be the sum of all the other constant terms on the right side. So it's just a plus c equals to 1. So since a equals to 1 over 3, so c equals to 1 minus 1 over 3, which is 2 over 3. Now we can substitute a, b, and c into this partial fractions, and then we can use that to start integrating. Now we can rewrite the original integral. So using the ABC we just found, let's copy it down and rewrite it. That equals to, I'll write it as like the sum of two separate integrals, one for this and one for that. So we have a is 1 over 3, that over x plus 1, and then dx, plus the integral of negative 1 over 3 x plus like bx plus c, right? So c is 2 over 3. Then last thing over x to the power of 2, and then minus x plus 1 dx. So this one is a lot easier to integrate, so we can do that directly. So we can pull out 1 over 3. So we only have 1 over x plus 1 here. Does that remind you of something? Probably the natural log, right? So we can just directly integrate it. And plus this thing copy down. We'll tackle this later because, well, it has a power of 2 here, right? It's more complicated. So let's do the first one. We have 1 over 3. And that is just, yeah. So it's ln absolute value of x plus 1 dx. Remember, we put the absolute value signs here because we just want to make sure ln something, like the something is just greater than 0, right? And that, like, from here to here, well, that is in the formula booklet. So yeah, it's very straightforward. Now we just copy this down again. So now we want to focus on tackling this one because we are already done with this one. So I'll copy this down. Plus, well, the numerator looks really messy. So like we want to pull out like a factor, right? So actually we should pull out negative 1 over 6. And you will see why. Instead of negative 1 over 3, we should pull out negative 1 over 6. And so we'll end up with, in the numerator, 2x minus 4, right? And then we have x squared minus x plus 1 dx. So if you observe the denominator, you will see that if you derive that, you will have like 2x minus 1, right? So since if you derive this, you have 2x minus 1, that's why I want to keep 2x minus something in the numerator, because it will help us with use substitution. So now we have 2x minus 4 instead of 2x minus 1. So why don't we just write this integral into the sum of two other integrals? So that becomes x minus 1 over x squared minus x plus 1 minus 3 minus the integral of 3 and then over x squared minus x plus 1 dx. Oh, I forgot dx. So now this can be solved by use substitution, and this thing will need something called completing the squares. And for completing the squares, there's a formula in the booklet for that, and I will show you what that looks like. So let's start solving this part. I'll just copy it here to make the headings. So as I've said, it's use substitution. So let's let u equals to x squared minus x plus 1. So du dx, which means if you derive it, you have 2x minus 1. So du equals to 2x minus 1 times dx. You have 2x minus 1 here, you have dx here. So this is just du, right? And this is just u. So like you have something really simple if you just put u inside. So this thing becomes you have, well, 1 over u du, right? So that should remind you of the natural log again. So like we can just keep doing it. Ln of absolute value of u plus c, right? And let's write the substitution for u. So that's just this. Well, we don't really need plus c here, actually, because like for the final big integral, so like that one will have c, so like it's okay if you don't write c right now, but like I'll put it here just for clarity. So notice that this thing is always positive, right? So you actually don't need the absolute signs right now. You can just write it like this. That is fine. So this thing is, like this thing inside ln is actually positive because, well, if x is 0, then you'll just have 1, which is positive. If x is a positive value, then x squared minus x must be greater than 1. Oh, sorry, must be greater than 0, and plus 1, which is makes it still positive. And if it's a negative value for x, then this is positive, this is positive, and this is positive, so like it's still positive. So that's why we don't need absolute value signs for now. You don't have to write plus c, so I won't write it here because we'll write it in the final answer. So now we should move on to solving the other part, which is 3 over that quadratic expression. So we can complete a square for the bottom, like the denominator, and apply a formula in the data booklet. We haven't been using it for now, I think, but like it's in there and you will probably use it later, so it's really useful to know how to use it. So the denominator equals to, if we want to complete a square, so we have x to the power of 2, right, minus x, so that is like 2 times x times something, right? That should be negative 1 over 2, right? So here we have x to the power of 2, so now we should also have negative 1 over 2 to the power of 2, right? So that becomes plus 1 over 4. And since we have 1 here, so we should add 3 over 4 here. This skill is something you must know, so like be sure you review and keep in mind how to do completing this square. So we end up having x minus half to the power of 2 plus 3 over 4. And we can write this as x minus half to the power of 2 plus, that's square root of 3 over 2 to the power of 2. So the reason we do this is because in the formula booklet, there's a formula that looks like, let me write it down. So on page 10, so this thing, so you have a square here and a square here, right? So that thing equals to 1 over a arctan, which is inverse of tan. It's x over a plus c. So we need to like use this formula. So first we are preparing it by making the denominator looks like a square plus a square, right? So now let's rewrite this and start using the formula. So that equals to 3 over the sum of this. Dx. Oh, we can pull 3 outside, right? So we have like 1 as the numerator numerator on top. So we have 3 times something. So let's see, like 1 over 8, right? A is this one. It's like the constant. So 1 over, we can simplify that later. And arctan of the, so it's like x over a, right? So x is just x minus half, and a is still that thing we just wrote, this fraction. I'm not gonna write plus c right now because we'll write it in the end, so we can just start simplifying that because it looks incredibly messy. So you just multiply the numerator by 2, you have 2x minus 1. That's over square root of 3. We can simplify that. So in the end, we just have 2 times the square root of 3 and then times this thing. So now we actually solved for all the separate parts, and let's just put them together, make sure they're multiplied by their fractions and in the correct signs. So, well, let's just assemble everything and you will get the final answer. So, we need to substitute what we got for that and what we got for that, and like assemble all of this together and plus c in the end. So just be very cautious, don't make an error in there. So like let's rewrite the original integral. Equals to, we already have this part, 1 over 3 ln of the absolute value of x plus 1. So now we're dealing with this part inside, minus 1 over 6 times, oh, that's a big thing inside. So we have ln, the first part is like this, right? So ln of a quadratic then minus this thing. So I'll just copy it down. I need to write it smaller because there's not a lot of space. This question is taking a full page. That's why it won't appear in IB, because no test question will be extremely long like this in paper 1 or paper 2. Yeah, and by the way, it's a single question. It's not like a part A, part B, part C question. So like IB won't test you something like this. It will test like 1 or 2 focused skills. Like maybe there will be like a complex question of just use substitution, but not like 4 skills together, right? So that's just ln of this thing. This quadratic. So this and this, well, we have positive, so that's right. Yeah, because we have like square root of 3 over 3, that is just 1 over square root of 3, right? So yeah, so this and just arctan of that thing inside. plus C. That's like you need to you need to write plus C to score full marks, right? So yeah. So that's the entire thing. It's quite long, right? But I think it's a really good practice.